edge of reason in the halls of math. Equations untangled like a genius's wrath. 7 riddles haunt the academic night. In shadows they linger out of pure spite. Unsolved millennium, don't you see? Whispers of infinity as wild as can be. Dance on the numbers, spirals end and start. Hold like a key to the universe's heart. A prisoner's dream in a realm untold. Rieman's ghost in the Zeta fold. P versus NP, who will take the crown in this mental race, wearing logic's gown. Imprisoned answers through a lattice maze. In the mirror, truth with Daly's days. Grasp the theorem, dream it wide and far. Mysteries untangled under the cosmic star. Unsolved millennium, don't you see? Whispers of infinity as wild as can be. Dance on the numbers, spirals end and start. Hold like a key to the universe's heart. Quantum loops in a quixotic ride. Ghosts of Godel, they will not abide. Mathematical beasts in shadows lair. In every fractal path truth lays bare. Unsolved millennium, don't you see? Whispers of infinity as wild as can be. Dance on the numbers, spirals end and start. Hold like a key to the universe's heart. Quantum loops in a quixotic ride. Ghosts of Gödel, they will not abide. Mathematical beasts in shadows lair. In every fractal path, truth lays bare. Unsolved millennium, don't you see? Whispers of infinity as wild as can be. Dance on the numbers, spirals end and start. Hold like a key to the universe's heart. I'm tasting answers to a lattice maze. In the mirror of truth where theories days. Grasp the theorem, dream it wide and far. Mysteries untangled under the cosmic star. Quantum loops in a quixotic ride. Ghosts of Gödel, they will not abide. Mathematical beasts in shadows lair. In every fractal path truth lays bare.
I, founder being of sound mind and memory, do hereby depose and say as follows. Introduction. This affidavit pertains to the Journal of Landing Across Linguistic Foreground, Issue 1, Unsolved Millennium Solutions, hereinafter referred to as the issue, a collection of essays and accompanying appendices. The issue explores various approaches to addressing the 7 Millennium Prize problems and other significant unsolved mathematical and philosophical challenges. Essay. The core of the issue is a comprehensive essay that examines the nature of language, its limitations, and its potential as a tool for exploring and solving complex problems. The essay argues that by carefully analyzing and manipulating linguistic structures, we can gain new insights into the underlying principles of reality. Appendices. The journal includes 10 appendices, each containing a manual that describes a unique computational approach to one of the Millennium Prize problems or a related area of inquiry, and an equation notation table of 90 symbols as the last appendix.
This inaugural issue of the Journal of Landing Across Linguistic Foreground embarks on a unique exploration of the interplay between language, cognition, and the pursuit of knowledge, with a specific focus on tackling some of humanity's most enduring intellectual challenges, the Millennium Prize problems. Recognizing the limitations of traditional mathematical and scientific approaches, we propose a novel framework that leverages the inherent flexibility and expressive power of language to generate novel insights and potential solutions. Drawing inspiration from the concept of synchronicity as articulated by David J. Hand, we acknowledge the inherent improbability of many significant discoveries. However, rather than attributing these events to mystical forces, we posit that they arise naturally from the interplay of vast information spaces and the inherent randomness of the universe. This perspective informs our approach, encouraging us to embrace serendipity and explore unexpected connections between seemingly disparate concepts. The cornerstone of this issue lies in the appendixes of the Augmented Assumption Dictionary, Millennium Solutions Beyond Memory, a compendium of innovative conjectures and conceptual frameworks specifically designed to address these complex problems. This dictionary, a key feature of this issue, presents a diverse range of excerpts, starting from Lang's conjecture in algebraic geometry to the Pauli-Young conjecture bridging psychology and quantum mechanics. These conjectures exemplify the power of creative hypothesis-driven inquiry. By challenging established assumptions and venturing into uncharted territories of thought, we aim to stimulate new avenues of investigation and potentially unlock breakthroughs in our understanding of the universe. Furthermore, we introduce the concept of K equals FB, A, C, E, a model that formalizes the intricate relationship between knowledge acquisition, base information, implicit assumptions, contextual factors, and cognitive effort. This model serves as a foundational framework for analyzing how we extract meaning from information and how our inherent biases and assumptions shape our understanding of the world. Finally, we explore the intriguing concept of unified reality, a philosophical perspective that posits the mind and the physical world as different facets of a single, underlying reality. Drawing upon the insights of thinkers like Spinoza and Kant, we examine the implications of this perspective for our understanding of consciousness, the nature of reality itself, and the potential for a more holistic approach to knowledge. This inaugural issue invites the reader on a journey of intellectual exploration, challenging conventional thinking and encouraging a deeper appreciation for the power of language, the importance of creative conjecture, and the profound interconnectedness of all knowledge. Outro essay. Synchronicity is an attempt to come up with an explanation for the occurrence of highly improbable coincidences between events where there is no causal link. It's based on the premise that existing physics and mathematics cannot explain such things. This is wrong, however standard science can explain them. That's really the point of the improbability principle. What I have tried to do is pull out and make explicit how physics and mathematics, in the form of probability calculus, does explain why such striking and apparently highly improbable events happen. There's no need to conjure up other forces or ideas, and there's no need to attribute mystical meaning or significance to their occurrence. In fact, we should expect them to happen, as they do, purely in the natural course of events. David J. Hand. As we conclude our exploration of the Augmented Assumption Dictionary, Millennium Solutions Beyond Memory, it becomes evident that the pursuit of knowledge is inextricably linked to the power of conjecture. It is through the formulation and testing of hypotheses that we advance our understanding of the world. The conjectures presented within these pages serve as beacons, guiding us towards new frontiers of thought and discovery. By delving into the realm of the unknown, we challenge the status quo and ignite the spark of innovation. Conjectures, while often speculative, provide a fertile ground for the cultivation of novel ideas. They encourage us to think critically, to question assumptions, and to seek evidence. In doing so, they propel us forward, expanding the boundaries of human knowledge. Lang's conjecture is a complex mathematical problem in algebraic geometry that deals with the distribution of rational points on algebraic varieties. Essentially, it asks how many solutions to polynomial equations with rational coefficients exist. Rational points are points on a curve or surface whose coordinates are rational numbers. An algebraic variety is a geometric object defined by polynomial equations. Lang's conjecture posits that for certain types of algebraic varieties, the number of rational points is either finite or grows slowly. Augmented versions of this conjecture involve adding specific conditions to the variety or the field of coefficients to obtain stronger results. The Pauli-Jung conjecture is a fascinating bridge between psychology and physics. It suggests a connection between archetypal patterns, universal primordial images or ideas inherent in the human psyche, and quantum mechanics, the fundamental theory of physics describing the behavior of matter and energy at the atomic and subatomic level. Augmented versions of this conjecture explore specific connections between archetypes and quantum phenomena, develop mathematical frameworks to describe their relationship, and combine insights from various disciplines to gain a deeper understanding. K equals FB, A, C, E. K, knowledge derived from a text or information. B, base knowledge or explicit information. A, implicit assumptions and inferences. C, contextual factors, cultural, historical, social. E, cognitive effort and analytical skills of the reader-interpreter. F, a complex function that integrates these variables to produce the final knowledge. Breaking down the function f can be further decomposed into several subfunctions. One assumption identification function identifies implicit assumptions based on linguistic cues, world knowledge, and logical reasoning. Can be modeled using techniques like natural language processing, machine learning, or knowledge graph analysis. 2. Assumption evaluation function assesses the validity and relevance of identified assumptions. Involves factors like consistency, coherence, and empirical evidence. 3. Contextual interpretation function considers the broader context, including cultural, historical, and social factors. Involves understanding cultural nuances, historical references, and social norms. 4. Cognitive effort function accounts for the cognitive effort required to process the information, including factors like text complexity, reader's prior knowledge, and attention span. This equation highlights the iterative and interdependent nature of the knowledge acquisition process. By considering multiple factors and their interactions, we can gain a more comprehensive understanding of how implicit assumptions influence our interpretation of information. Unified reality, the theory proposes that the mind and the physical world are not separate entities, but rather different facets of a single, fundamental reality. 2 perspectives, this underlying reality can be viewed from 2 perspectives, the mental and the physical. These perspectives are not reducible to each other, but they are interconnected and interdependent. Mind-body problem, the double aspect theory offers a solution to the mind-body problem, a long-standing philosophical question about the relationship between the mind and the physical body. It avoids the pitfalls of both materialism, which reduces the mind to physical processes, and dualism, which posits 2 separate substances, mind and matter. Spinoza, a prominent proponent of this view, Spinoza argued that the mind and body are two attributes of a single substance, known as substance or God or nature. Kant, while not explicitly endorsing the double aspect theory, Kant's philosophy suggests that the mind and the physical world are interconnected and interdependent, arising from a deeper, unified reality. Schopenhauer proposed that the world is fundamentally a manifestation of a single, unconscious will, which can be experienced both as the physical world and as subjective mental states. Explaining consciousness, the theory struggles to explain the subjective nature of consciousness and how it arises from the underlying reality. The nature of the underlying reality remains elusive and difficult to define. Empirical evidence, the theory lacks direct empirical support and relies on philosophical arguments and intuition. A Laurent series is a mathematical series that represents a complex function as a sum of positive and negative powers of a complex variable z1. It's a powerful tool in complex analysis, particularly useful for analyzing functions around isolated singularities. Given a complex function fz and an annulus centered at z with inner radius r and outer radius r2, the Laurent series expansion of fz in this annulus is given by neutralizing zeros and Laurent series. The concept of neutralizing zeros is not a standard term in complex analysis. However, it might refer to techniques used to manipulate the behavior of a function around its singularities. Here are some potential interpretations and their connection to Laurent series. Removable singularities. If a function fz has a removable singularity at z, it means that the limit of fz as z approaches z exists. In this case, the Laurent series of fz around z will have only non-negative powers of z, and the coefficient of the z superscript 1 term will be 0. This can be thought of as neutralizing the singularity by defining the function at z to be the limit value. Poles. If fz has a pole of order m at z, the Laurent series will have a finite number of negative powers of z, up to the power of m. Techniques like residue calculus can be used to analyze the behavior of functions with poles, and in some cases, it might be possible to neutralize the pole by multiplying the function by a suitable factor to cancel the singular term. Essential singularities. Essential singularities are the most complex type of singularity. The Laurent series of a function with an essential singularity at z has infinitely many negative powers of z. Neutralizing essential singularities is generally not possible, as their behavior is highly unpredictable and complex. Advanced techniques in complex analysis, such as conformal mapping, residue calculus, and analytic continuation, can be used to manipulate functions and their Laurent series expansions. A prolonged meditation on the subject has satisfied me that the existence of any one such odd perfect number, its escape, so to say, from the complex web of conditions which hem it in on all sides, would be little short of a miracle. James Joseph Sylvester. 0, 6, 28, 496 and 8128. 2 is the only even prime number. 1. All other prime numbers are odd. Sure, here is an equation to represent the sum of proper positive divisors of a number n. Sum of proper positive divisors n equals sigma n equals p1 plus p2 plus pn, where p1, p2, pn are the positive prime factors of n. Now, an odd perfect number is defined as a number that is equal to the sum of its proper positive divisors, so we can write this equation for an odd perfect number. Odd perfect number n equals sum of proper positive divisors n equals sigma n. The problem of finding odd perfect numbers is a long-standing unsolved problem in mathematics. While there are many properties that an odd perfect number must satisfy, no one has yet been able to prove or disprove their existence. The formula you provided, n equals sigma n, is the definition of a perfect number, whether even or odd. However, it does not provide a direct way to find a specific odd perfect number, let alone the billionth one. Currently, the smallest odd perfect number, if it exists, is known to be greater than 10,500. This means that we are still very far from finding the billionth odd perfect number, even if we knew how to find the first one. Any odd perfect number must be enormous, exceeding 2,000 digits. It requires at least 101 prime factors, including at least 9 distinct ones. Additionally, it must have a prime power divisor with a length of over 62 digits. Descartes discovered a number, 1985855761189, which is remarkably close to being perfect. It's known as an odd spoof perfect number because, while it's not perfect, it shares some properties with perfect numbers. But Descartes discovered one odd number that's very close to being perfect, the odd spoof perfect number. Volunteer-powered, GIMPs relies on volunteers who donate their idle computing power to run the Prime 95 software. Significant discoveries, GIMPs has been responsible for discovering several world record-breaking prime numbers. Open source, the software used in GIMPs is open source, allowing anyone to contribute to the project. Euler's theorem on odd perfect numbers, n equals pkm2. Where p is a prime number congruent to 1 mod 4. K is a positive integer. M is an integer not divisible by p. In the representation of odd perfect numbers given by n equals p lambda m2, the exponent lambda is related to Mersenne prime p according to the formula p lambda equals 2q, 1, where q is also a positive integer. It identifies the connection between Mersenne primes and odd perfect numbers. Euler's theorem advanced, if an odd perfect number exists, it must be of the form p alpha q1 2 beta 1 q2 2 beta 2. Qk 2 beta k, where p, q1, q2, qk are distinct primes, alpha is odd, and beta 1, beta 2, beta k are positive integers. If n is an odd perfect number, it must be of the form n equals p alpha k superscript 2, where p is a prime number, alpha is an odd positive integer, k is a positive integer, and p does not divide k. Divisibility tests, while not directly related to finding odd perfect numbers, divisibility tests can help in the search by quickly eliminating numbers that are not divisible by certain primes. Divisibility by 2. A number is divisible by 2 if its last digit is even. Divisibility by 3. A number is divisible by 3 if the sum of its digits is divisible by 3. Divisibility by 5. A number 1 is divisible by 5 if its last digit is 0 or 5. 2. Prime factorization is essentially breaking down a number into its building blocks, where each block is a prime number. A prime number is a natural number greater than 1 that has no positive divisors other than 1 and itself. 1 divided by 2, 30 divided by 2 equals 15, so 2 is a factor. 2 divided by 3, 15 divided by 3 equals 5, so 3 is a factor. 5 is a prime number, we've reached a prime number, so 5 is the last factor. Therefore, the prime factorization of 30 is 2 times 3 times 5. Why prime factorization matters: finding the greatest common divisor GCD and least common multiple LCM of two numbers. Encrypting and decrypting data. 1. Trial division iteratively checks divisibility of a number by all primes less than or equal to its square root. While simple, it can be slow for large numbers. 2. Will factorization precomputes a list of small primes and uses them to quickly eliminate multiples of those primes. More efficient than trial division, especially for larger numbers. 3. Pollard's row algorithm can be used to find prime factors of large numbers. It can be used to factorize numbers and identify prime factors. 4. Quadratic sieve can be used to factorize large integers, including numbers with hundreds of digits. It can be used to factorize numbers and identify prime factors. 5. Number field sieve can factorize very large numbers, including those with hundreds of digits. It can be used to factorize numbers and identify prime factors. This equation follows the pattern of expressing a prime number of the form 4k plus 1 as the sum of two squares. 29 is a prime number that fits this form. 29 equals 47 plus 1, and it can be represented as the sum of the squares of 2 and 5. A perfect number is a positive integer that is equal to the sum of its proper positive divisors. For example, 6 is a perfect number because its divisors are 1, 2, and 3, and 1 plus 2 plus 3 equals 6. Number theoretic properties. Exploiting number theoretic properties can help in identifying potential prime candidates. For example, all primes greater than 3 are of the form 6k plus or minus 1. By focusing on numbers of this form, we can reduce the search space. For very large numbers, deterministic primality tests can be computationally expensive. Probabilistic primality tests, like the Miller-Rabin test, can quickly determine with high probability whether a number is prime or composite. You have no compelling moral intuitions to guide you in solving that problem. Your moral feelings are attached to frames, to descriptions of reality rather than to reality itself. Daniel Kahneman. The Collatz conjecture, also known as the 3n plus 1 conjecture, the 3x plus zone problem, The 3x plus zone problem, or the uudekadigit problem, is a conjecture in mathematics. Its statement, based on a simple function applied to an integer, is easy to understand, but its status is the subject of deep conjectures and intense mathematical research. The conjecture is generally believed to be true for all positive integers, but a formal proof eludes even the concerted efforts of modern mathematicians. 1. Start with any positive integer, choose any number you like, for example, 7. 2. Apply the rule. If the number is even, divide it by 2. If the number is odd, multiply it by 3 and add 1. 3. Repeat the process, continue applying the rule to the resulting number. 7 is odd, so we calculate 3. 7 plus 1 equals 22. 22 is even, so we divide by 2, getting 11. 11 is odd, so we calculate 3. 11 plus 1 equals 34. 34 is even, so we divide by 2, getting 17. And so on. The conjecture states that, no matter which positive integer you start with, this process will eventually lead to the number 1. Is the 12th consonant in the Hindi alphabet. To pronounce it, the tip or middle of the tongue is placed against a part of the palate. It's classified as a nunaspirated and voiced consonant in Hindi phonetics. Great sound or cosmic sound, referring to the primordial sound or vibration. Celestial sphere, the sphere of the moon or Sunday. Circle or sphere, a general term for a circular or spherical shape. Enclosure or boundary, a limit or surrounding area. Zero or nothingness, the absence of any quantity. Perceptible or observable, something that can be perceived by the senses. From Shabdakosh.com, the website provides definitions for in Hindi, including its association with Shiva, great sound, celestial spheres, and more. The consonant is the 12th consonant in the Hindi alphabet. To pronounce it, the tip or middle of the tongue touches a part of the palate. It's classified as a nunaspirated and voiced consonant. Shiva, a Hindu deity. A great sound or cosmic vibration. The celestial sphere of the moon or sun. A circle or sphere. An enclosure or boundary. Zero or nothingness. Something that can be perceived by the senses. Shabdakosh.com provides definitions for in Hindi, including its association with Shiva, great sound, celestial spheres, and more. Wiktionary offers a detailed explanation of its pronunciation and placement within the Hindi phonetic system. Uudika likely refers to the number 12, as dodika is a prefix meaning 12. Digit refers to a single symbol used to represent a number. So, a uudekadigit could potentially refer to a single symbol representing a number in a base 12 system. Mx equals 3mx plus f, 1 2 n where, mx is a function that represents the Collat sequence starting from the initial number x. N is the number of steps in the Collat sequence for the given value of x. F is a constant that remains undetermined. Here's a breakdown of what this equation is trying to do. The Collat's conjecture states that if you start with any positive integer, you will eventually reach the number 1 if you apply the following process: 1 if the number is even, divide it by 2. 2 if the number is odd, multiply it by 3 and add 1. This process generates a sequence of numbers called the Collat sequence. For example, the Collat sequence for the number 6 is 6, 3, 10, 5, 16, 8, 4, 2, 1. If this formula could be solved for all values of x, it would prove the Collat's conjecture. However, this has not yet been achieved. The significance of this equation lies in the fact that it highlights the complexity of the Collatz conjecture. Even though the process of generating the Collatz sequence seems simple, finding a mathematical formula to describe it has proven to be extremely difficult. Ulam's packing conjecture, named after Stanislav Ulam, is a conjecture about the highest possible packing density of identical convex solids in three-dimensional Euclidean space. The conjecture says that the optimal density for packing congruent spheres is smaller than that for any other convex body. Imagine trying to pack as many identical objects as possible into a box. Ulam's conjecture suggests that spheres like balls are the worst shape for packing. No matter what other shape you choose, as long as it's convex, you can always pack it more densely than spheres. It's a fundamental question in geometry and has implications in various fields, from materials science to logistics. It challenges our intuition about shapes and space. While it seems counterintuitive, there's mathematical evidence to support this idea. The conjecture is still open, meaning it hasn't been proven or disproven. There have been significant advancements in understanding packing problems, but a complete solution to Ulam's conjecture remains elusive. Recent research has shown that spheres are indeed locally the worst packing shape among certain classes of convex bodies. Packing density PD is defined as the ratio of the volume occupied by the spheres to the total volume of the container. Conscious experience is at once the most familiar thing in the world and the most mysterious. There is nothing we know about more directly than consciousness, but it is far from clear how to reconcile it with everything else we know. Why does it exist? What does it do? How could it possibly arise from lumpy gray matter? We know consciousness far more intimately than we know the rest of the world, but we understand the rest of the world far better than we understand consciousness. Consciousness can be startlingly intense. It is the most vivid of phenomena, nothing is more real to us. But it can be frustratingly diaphanous. In talking about conscious experience, it is notoriously difficult to pin down the subject matter. The International Dictionary of Psychology does not even try to give a straightforward characterization. Consciousness, the having of perceptions, thoughts, and feelings, awareness. The term is impossible to define except in terms that are unintelligible without a grasp of what consciousness means. Many fall into the trap of confusing consciousness with self-consciousness. To be conscious, it is only necessary to be aware of the external world. Consciousness is a fascinating but elusive phenomenon. It is impossible to specify what it is, what it does, or why it evolved. Nothing worth reading has been written about it. Sutherland, 1989. David J. Chalmers, The Conscious Mind, in Search of a Fundamental Theory. The universe's lumpy matter refers to the uneven distribution of matter on large scales. While the universe is homogeneous and isotropic on the largest scales, meaning it looks the same in all directions and at all points, on smaller scales, matter is clustered into galaxies, galaxy clusters, and superclusters. This lumpy structure is thought to have originated from tiny fluctuations in the density of the early universe. These fluctuations were amplified by gravity, causing matter to clump together over billions of years. The result is the cosmic web, a vast network of filaments and voids that fills the universe. The lumpy nature of the universe has important implications for our understanding of cosmology, including the nature of dark matter and dark energy. It also raises questions about the initial conditions of the universe and the mechanisms that led to the formation of large-scale structures. Grid-based simulations. These simulations divide space into a grid of cells. Each cell can be assigned a binary value to represent the presence or absence of matter. This binary representation allows efficient storage and computation. Particle-based simulations. In these simulations, individual particles of matter are tracked. Their positions and velocities can be represented using binary numbers, especially when using floating point representations. Binary data formats. Astronomical data, like images from telescopes, can be stored in binary formats. Each pixel in an image can be represented by a binary number, encoding its intensity. Data compression. Techniques like lossless compression use binary algorithms to reduce file size without losing information. This is crucial for handling large astronomical data sets. Fractals and chaos theory. Some cosmological structures exhibit fractal-like patterns, where similar patterns appear at different scales. Fractals can be described using mathematical equations, and binary numbers can be used to represent fractal dimensions. Cellular automata. These are simple models that can generate complex patterns. They often involve binary rules for cell state updates, and can be used to study the emergence of structure in the universe. While the lumpy matter distribution itself isn't directly expressed in binary equations, the tools and techniques used to study and simulate it heavily rely on binary principles. The binary representation of information allows for efficient storage, computation, and analysis of the complex structures of the universe. The Boltzmann equation is a fundamental equation in statistical mechanics that describes the time evolution of a system of particles. In cosmology, it's used to model the distribution of matter and radiation in the early universe. A simplified form of the Boltzmann equation for a single particle species is Ft plus Bf plus Fb equals Cf. F, distribution function, which describes the number density of particles in a given phase space volume. B, velocity of the particle. F, force acting on the particle. Cm, collision integral, which accounts for particle interactions and scattering processes. The Weyl potential, which is the sum of the spatial and temporal distortions of the universe's geometry, provides a direct way of testing the theory of gravity and the validity of the lambda CDM lambda cold dark matter model. Here we present measurement of the Weyl potential at 4 redshift spans using data from the first 3 years of observations of the dark energy survey. We find that the measured Weyl potential is 2 sigma, respectively 2.8 sigma, below the lambda CDM. Predictions in the 2 lowest redshift bands. We show that these low values of the Weyl potential are at the origin of the tension between cosmic microwave background measurements and weak lensing measurements, regarding the parameter sigma 8, which quantifies the clustering of matter. Interestingly, we find that the tension remains and no information from the cosmic microwave background is used. Dark energy survey data on their own prefer high value of the primordial fluctuations, together with the slow evolution of the wave potential. An important feature of our method is that the measurements of the wave potential are model independent and can therefore be confronted with any period of gravity, allowing efficient tests of models beyond general relativity. To sauce, Python bit, CN Grim, and 2024. Measurement of the wave potential emission from the first 3 years of dark energy survey data. Nature Communications, 15-1, 9295. The four-body problem is a notoriously complex problem in celestial mechanics that involves predicting the motion of four celestial bodies interacting gravitationally. Unlike the two-body problem, which has a closed-form solution, the four-body problem and higher-body problems generally do not have exact analytical solutions. However, we can formulate the equations of motion for the four-body problem using Newton's laws of motion and Newton's law of universal gravitation. Consider four bodies with masses m, m2, m3, and m4, and position vectors r, r2, r3, and r4, respectively. The equations of motion for each body can be written as While this equation is highly complex, it provides a framework for understanding the evolution of the universe, from the initial Big Bang to the formation of large-scale structures like galaxies and clusters. Beyond a gray or black box. In the context of the Einstein field equations, they are often considered a white box model, as the underlying mathematical structure and physical principles are well understood. If P equals NP, then the world would be a profoundly different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Scott Aronson, UT Austin. The question is, are P and NP the same? If so, it would mean that any problem that can be quickly verified can also be quickly solved. However, most computer scientists believe that P is not equal to NP. P polynomial time, a class of problems that can be solved by a deterministic algorithm in polynomial time. This means the time it takes to solve the problem increases polynomially with the size of the input. NP non-deterministic polynomial, a class of problems for which a solution can be verified in polynomial time by a deterministic algorithm. This means if you're given a potential solution, you can quickly check if it's correct. Binary is the foundation of computer science, and many NP problems involve searching through a vast space of binary possibilities. For example, the traveling salesman problem involves finding the shortest possible route that visits each city exactly once. This can be represented as a binary decision problem, whether a particular route is shorter than a given threshold. Tuples can be used to represent solutions to NP problems. For instance, in the knapsack problem, a tuple can represent the items included in the knapsack. While less common, ternary logic can be used to represent certain types of problems, and ternary computers could potentially offer advantages in certain scenarios. If P equals NP, it would have profound implications for many fields, including, many cryptographic algorithms rely on the assumption that certain problems are hard to solve. If P equals NP, these algorithms could be broken. NP problems are central to AI, and solving them efficiently could lead to significant advancements. Many optimization problems, such as scheduling and logistics, are NP hard. Efficient solutions could revolutionize industries. If there really were a machine with phi n kn or even kn2, this would have consequences of the greatest importance. Namely, it would obviously mean that in spite of the undecidability of the Entscheidungsproblem, the mental work of a mathematician concerning yes or no questions could be completely replaced by a machine. After all, one would simply have to choose the natural number n so large that when the machine does not deliver a result, it makes no sense to think more about the problem. Kurt Gödel. If you imagine a number m that's finite but incredibly large, like say the number 10(3) discussed in my paper on coping with finiteness, then there's a humongous number of possible algorithms that do nm bitwise or addition or shift operations on n given bits, and it's really hard to believe that all of those algorithms fail. My main point, however, is that I don't believe that the equality P equals NP will turn out to be helpful even if it is proved, because such a proof will almost surely be non-constructive. Donald Knuth. The Axe Primality test, developed by Manindra Agrawal, Neeraj Kyle, and Nitin Saxena in 2002, is a deterministic algorithm that can determine whether a given number is prime or composite in polynomial time. This was a significant breakthrough in computational number theory, as it provided the first provably efficient algorithm for primality testing. The VP versus VNP problem is a fundamental question in algebraic complexity theory, analogous to the PVS. The theory involves concepts from algebra and circuit complexity. Arithmetic circuits, which are the algebraic analog of Boolean circuits, play a crucial role in defining the complexity classes VP and VNP. These circuits use addition and multiplication gates to compute polynomials. The VP class consists of families of polynomials that can be computed by a polynomial size and degree. VNP is the class of polynomial families that can be defined as the sum of exponentially many monomials, each of polynomial degree. The VP versus VNP problem asks whether these two classes are equal, meaning whether every polynomial in VNP can be efficiently computed by a polynomial-sized arithmetic circuit. Madia thought that he and Alice were like that, twin primes, alone and lost, close but not close enough to really touch each other. Paolo Giordano. The twin prime conjecture is a famous unsolved problem in number theory that asks whether there are infinitely many pairs of prime numbers that differ by 2. These pairs are called twin primes. Examples of twin primes: 3, 5, 5, 7, 11, 13, 17, 19, 29, 31. The conjecture states that there are infinitely many such pairs. While mathematicians have made significant progress towards proving this conjecture, it remains unsolved. Euclid, in ancient times, Euclid proved that there are infinitely many prime numbers. De Polignac's conjecture: in 1849, Alphonse de Polignac made a more general conjecture, which includes the twin prime conjecture as a special case. Subsequent progress, researchers like James Maynard and Terence Tao have further reduced the gap between primes, bringing us closer to a potential proof of the twin prime conjecture. Twin paradox, a relativistic conundrum. Nature, a thought experiment in special relativity. Key concept: time dilation, a consequence of the theory of relativity. Methodology, relies on the principles of special relativity, particularly the concept of space-time. Involves analyzing the space-time paths of the two twins, considering factors like acceleration and changes in reference frames. Uses mathematical tools like Lorentz transformations to quantify the time dilation experienced by each twin. Resolution: the paradox is resolved by recognizing the asymmetric nature of the twins' journeys. One twin undergoes acceleration and changes reference frames, while the other remains in a single inertial frame. This asymmetry leads to a difference in the amount of time experienced by each twin, with the twin who undergoes acceleration aging less. The Yang-Mills theory aims to describe the strong, weak, and electromagnetic forces. It predicts the existence of massless particles called gluons, which mediate the strong force. However, mathematically rigorous proofs for the existence and mass gap, the minimum energy of a non-trivial quantum state of these particles, remain elusive. Imagine a theory that explains how fundamental particles interact. The Yang-Mills theory is a key part of this, but some crucial aspects, like the existence of certain particles and their minimum energy, haven't been fully proven mathematically. This notation is equivalent to the one you provided, but it emphasizes the quantifier infinitely many to explicitly state the infinite nature of the twin prime pairs. For any natural number n, there exists a prime number Pn such that p plus 2 is also prime. The prime number theorem gives us an estimate for the number of primes less than a given number, n. It states that there are approximately n log n. Irregularity: the distribution of twin primes is inherently irregular. While there are patterns and conjectures, the exact spacing between them remains unpredictable. Density: the density of twin primes decreases as we move further along the number line. This is somewhat analogous to the tail of a probability distribution, where the probability of extreme values decreases. Regularity: probability distributions, like the normal distribution or the standard normal distribution, describe the likelihood of different outcomes in a random process. Cumulative distribution function CDF: the CCDF you mentioned, CCDF z equals 1, indefinite integral from -infinity to z1 square root 2 pi exp minus 0.5 t superscript 2 dt, is a specific type of CDF for the standard normal distribution. It calculates the probability of a random variable being greater than a given value z. The irregularity in the distribution of twin primes can be seen as a kind of randomness in the prime number sequence. Probability distributions, on the other hand, provide a framework for understanding and quantifying randomness. The K-tuple conjecture, also known as the first Hardy-Littlewood conjecture, states that for any admissible K-tuple, there are infinitely many integers n such that all the values in the K-tuple are prime when n is substituted. John was able to establish that there exists an integer n less than 70 million such that there are infinitely many pairs of primes differing by n. Zhang's work heavily relied on the method developed by Goldstein, Pines, and Yildirim Gpy in 2005. This method involves studying prime tuples of the form n plus h1, n plus h2, n plus hk, where the high are fixed integer shifts. The GPY method aims to show that there are infinitely many n for which multiple elements of the tuple are simultaneously prime. Zhang introduced refinements to the GPY method. Bruns-Sieve, it involves a more sophisticated analysis of the distribution of prime numbers and their residues modulo various primes. Selberg-Sieve, a powerful sieve method that is more flexible than Bruns-Sieve. While more complex, it can provide sharper bounds and estimates for the distribution of twin primes. Bombiri-Vinogradov theorem, he utilized a stronger version of this theorem to handle prime number distribution in arithmetic progressions. Klosterman sums, he applied bounds on Klosterman sums to estimate certain error terms in the calculations. A collaborative effort known as the Polymath Project further refined the techniques and reduced the bound on the prime gap. Currently, the smallest known bound is 246, meaning there are infinitely many pairs of primes that differ by at most 246. For any positive even number n, there are infinitely many prime gaps of size n. In other words, there are infinitely many cases of two consecutive prime numbers with difference n. Alphonse de Polignac. At the death of Riemann, a note was found among his papers, saying these properties of zeta s. The function in question are deduced from an expression of it which, however, I did not succeed in simplifying enough to publish it. We still have not the slightest idea of what the expression could be. As to the properties he simply enunciated, some 30 years elapsed before I was able to prove all of them but one, the Riemann hypothesis itself. Jacques Hadamard, The Mathematician's Mind, 8. Paradoxical Cases of Intuition. The Riemann hypothesis is one of the most famous unsolved problems in mathematics. It was proposed by Bernhard Riemann in 1859 and asserts that all non-trivial zeros of the Riemann zeta function have a real part of 1, 2. This function is a complex function that has been studied extensively in mathematics and has connections to many other areas of mathematics, including number theory, analysis, and physics. The Riemann hypothesis has been verified for billions of zeros, but a proof of the hypothesis for all zeros has eluded mathematicians for over 160 years. If proven, the Riemann hypothesis would have profound implications for our understanding of the distribution of prime numbers and other mathematical concepts. It would also likely lead to advances in many other areas of mathematics and science. The Riemann zeta function, denoted by the Greek letter zeta zeta, is a mathematical function of a complex variable defined as zeta s equals sigma 1 ns or zeta s equals 1 1 s plus 1 2 s plus 1 3 s plus, where the sum extends over all positive integers n, and s is a complex number with real part greater than 1. This function was first studied by Leonhard Euler in the 18th century for real values of s, and later generalized by Bernhard Riemann to complex values. Analytic continuation: the Riemann zeta function can be analytically continued to a meromorphic function on the entire complex plane, except for a simple pole at s equals 1. Euler product formula: for complex numbers s with real part greater than 1, the zeta function can be expressed as an infinite product over all prime numbers. If you encounter an indeterminate form when directly substituting the limit value, you can differentiate both the numerator and the denominator separately and then re-evaluate the limit. This process can be repeated as needed until the indeterminate form is resolved. Therefore, the limit is 1. The Airy zeta function is a mathematical function analogous to the Riemann zeta function, but related to the zeros of the Airy function. It was studied by Richard Crandall in 1996. The Airy zeta function, denoted as zs, is defined as zs equals sigma 1 rs, where the sum is over all real negative zeros r of the Airy function aiz. This series converges when the real part of s is greater than 3 2, and can be extended to other values of s through analytic continuation. The Lefschetz trace formula is a powerful tool in algebraic geometry that relates the topology of a variety to its arithmetic properties. In the context of zeta functions, it connects the number of points of a variety over finite fields to the eigenvalues of the Frobenius morphism acting on the Adel cohomology of the variety. The formula essentially states that the zeta function can be expressed as a product of determinants involving the eigenvalues of the Frobenius morphism acting on the cohomology groups of the variety. These eigenvalues encode information about the number of points of the variety over finite fields. The infinite product formula provides a more direct expression for the zeta function in terms of the closed points of the variety. An Agassiz zeta function is a type of generating function that counts the number of solutions of a polynomial equation, modulo powers of a prime number. It's a powerful tool in number theory and arithmetic geometry, offering insights into the arithmetic properties of algebraic varieties. This Euler product provides a deep connection between the Riemann zeta function and the distribution of prime numbers. It can be used to derive various properties of the zeta function, such as its zeros. The Audley-Koskoniag algorithm was a significant advancement in computational number theory, allowing for the efficient calculation of the Riemann zeta function at many points. This breakthrough enabled Andrew Audley's-Co to compute millions of non-trivial zeros of the zeta function at extremely high heights, around 1020. By analyzing the distribution of these zeros, Audley's-Co found compelling evidence supporting the GU conjecture. This conjecture suggests a deep connection between the spacing of the zeros of the Riemann zeta function and the eigenvalues of large random matrices from the Gaussian unitary ensemble GU. As more zeros are computed and analyzed, the statistical patterns observed in their distribution align more closely with the predictions of random matrix theory. This growing body of numerical evidence strengthens the belief in the GU conjecture and its potential implications for the Riemann hypothesis. This elegant formula connects the seemingly disparate worlds of infinite series and geometry. Specifically, the value of pi Euler's proof of this result in the 18th century was a significant breakthrough, demonstrating the power of mathematical analysis. One of the most striking connections is the relationship between Bernoulli numbers and the values of the Riemann zeta function at even positive integers. Specifically, for even positive integers 2n, we have Despite the vast conceptual gulf separating Babson from the new generation of relativists, we are left with intriguing, and perhaps ironic associations. By organizing conferences, sponsoring the annual essay contests, and making money and enthusiasm widely available for people interested in gravity, the Eccentric Gravity Research Foundation may claim at least some small amount of the credit for helping to stimulate the post-war resurgence of interest in gravitation and general relativity. David Kaiser. The Hellings-Downs curve is a critical tool in gravitational wave research, particularly for detecting a stochastic gravitational wave background (SGWB). It's not directly related to antigravity, but it's a significant step in understanding gravitational waves, which are ripples in the fabric of space-time caused by massive cosmic events like merging black holes or neutron stars. The Hellings-Downs curve, or overlap reduction function, helps scientists analyze correlations between pairs of pulsars to detect these gravitational waves. The NanoGrav team's 2023 publication used this curve to provide evidence for the SGWB by analyzing data from 67 millisecond pulsars over 15 years. The God Award is a prestigious prize offered by the God Stiftung God Foundation for groundbreaking research in gravitational manipulation. Established in 2004, the award challenges scientists and hobby researchers to demonstrate an experiment where an object weighing at least 20 grams floats freely for at least 1 minute, approximately 10 centimeters above a supporting surface, without relying on known phenomena like magnetism or buoyancy. The prize is €1 million, and the experiment must be replaceable and prove a direct influence on gravity. The goal is to encourage innovative approaches to understanding and potentially controlling gravity, a fundamental force that remains less understood compared to other forces like electromagnetism. Isaac Newton 1666, Newton's observation of an apple falling led to the formulation of the law of universal gravitation. Thomas Townsend Brown 1920s, Brown coined the term electrogravitics and claimed to have discovered an effect where high voltages could produce a force that appeared to counteract gravity. Nikola Tesla 1928, Tesla proposed a space drive that used electromagnetic fields to create propulsion, which some interpret as an early form of anti-gravity technology. Roger Babson 1948, founded the Gravity Research Foundation to study ways to reduce the effects of gravity. Yevgeny Podkletnov 1992, claimed to have created a device that could shield objects from gravity using a superconducting disk. NASA's Breakthrough Propulsion Physics Project 1996-2002, explored advanced propulsion concepts, including anti-gravity. Artificial gravity is typically created through centripetal force, which is the force that makes objects move in a circular path to simulate gravity is. A gravity hill, also known as a magnetic hill, mystery hill, or anti-gravity hill, is an optical illusion where a slight downhill slope appears to be an uphill slope. This makes objects like water, balls, or even cars seem to roll uphill against gravity. The illusion is usually caused by the surrounding landscape and the lack of a visible horizon. Magnetic hill in Moncton, Canada. Anti-gravity hill in Woodend, Australia. Into the quantum realm, where conventional understanding of gravity and other forces breaks down. While the Casimir effect demonstrates a tangible quantum force, anti-gravity theories aim to harness or manipulate quantum effects to counteract or neutralize gravity. Neutral buoyancy occurs when an object's average density is equal to the fluid in which it is immersed, making it neither sink nor float. This state is achieved when the upward buoyant force balances the downward gravitational force. It is used extensively in underwater training for astronauts. NASA, for example, uses large swimming pools called neutral buoyancy labs to simulate the microgravity environment of space. This allows astronauts to practice their tasks in conditions that closely resemble weightlessness. Weightlessness, or zero gravity, occurs when there is no net gravitational force acting on an object. This state is often experienced in free fall, such as in orbit around Earth, where objects are in continuous free fall towards the planet, but because they are moving forward at such a high speed, they perpetually miss it. Astronauts experience weightlessness aboard the International Space Station ISS as it orbits Earth. Similarly, weightlessness can be briefly experienced on Earth in parabolic flight maneuvers conducted by special aircraft, often referred to as vomit comets. Neutral buoyancy is generally achieved in a fluid medium like water, while weightlessness typically occurs in a vacuum or microgravity environment such as space. Neutral buoyancy involves balancing forces within a fluid, whereas weightlessness involves the absence of net gravitational forces, typically due to free fall conditions. Gyroscopic devices. These produce a force when twisted that operates out of plane, sometimes appearing to lift themselves against gravity. Despite being well understood as an illusion, many anti-gravity device claims have arisen from this effect. Herney Wallace patented devices involving rapidly spinning discs of brass, claiming they created a gravitomagnetic field. No independent testing or public demonstrations have validated these claims. A reported decrease in weight along the axis of a right-spinning gyroscope was tested in 1990, yielding null results. Thomas Townsend Brown's gravitator. Brown noticed that a high-voltage Coolidge tube seemed to change mass based on orientation. He developed devices combining high voltages and high dielectric constant materials, calling them gravitators. Brown claimed his devices showed anti-gravity effects and attempted to sell them to aircraft companies and the military. He coined the terms Biefeld-Brown effect and electrogravitics. Subsequent studies by R. L. Talley, NASA scientist Jonathan Campbell, and Martin Tajmer found no thrust could be observed in a vacuum, with results consistent with electrohydrodynamic effects rather than anti-gravity. Repulsive gravity is a hypothetical concept that suggests gravity can act as a repulsive force, pushing objects apart instead of pulling them together. This is contrary to our everyday experience of gravity as an attractive force. In some theoretical models, objects with negative mass could exist. According to general relativity, negative mass would experience a repulsive gravitational force with ordinary positive mass. In certain scenarios involving the emission of gravitational waves, a temporary repulsive gravitational force could arise. However, there is no experimental evidence for the existence of negative mass. Over the real numbers, 2 times 10 to the power of 6 is the quasi-split form of E6, and is one of the 5 real forms of E6 classified by Elia-Cartan. Its maximal compact subgroup is of type F4. This formula expresses the character of an irreducible representation of a compact Lie group in terms of Weyl group elements and weights. The Alcubierre drive is a speculative concept for a warp drive that could allow for faster-than-light travel. It's based on a solution to Einstein's field equations that involves manipulating space-time itself. 1. The drive creates a warp bubble around a spacecraft, compressing space-time in front of it and expanding it behind. 2. The spacecraft surfs the space-time wave, effectively allowing it to travel faster than the speed of light relative to distant observers. 3. The Alcubierre drive requires exotic matter with negative energy density, which is currently hypothetical. Energy requirements: the amount of energy needed to create and maintain a warp bubble is astronomical, far beyond our current technological capabilities. Control and safety: controlling and safely navigating a warp bubble would be extremely complex. The core equation behind the Alcubierre drive is the metric tensor, which describes the geometry of space-time. In the specific case of the Alcubierre drive, it's a solution to Einstein's field equations that allows for a warp bubble to form. There are, roughly speaking, two kinds of mathematical creativity. 1. Akin to conquering a mountain peak, consists of solving a problem which has remained unsolved for a long time and has commanded the attention of many mathematicians. The other is exploring new territory. Mark Casey. The Cambrian explosion saw a rapid diversification of animal life, driven by increased oxygen levels, complex ecosystems, and genetic innovations. The Ordovician radiation diversified marine life post-extinction. The Devonian explosion was the age of fishes, with land colonization by plants and arthropods. The Carboniferous rainforest collapse was a major extinction due to climate change. The Permian-Triassic extinction was Earth's largest, caused by volcanic eruptions and climate change. The Triassic-Jurassic extinction cleared the way for dinosaurs. The Cretaceous-Paleogene extinction wiped out non-avian dinosaurs via asteroid impact, and the Cenozoic radiation diversified mammals, birds, and plants post-dinosaur extinction. Monotheism and polytheism are two fundamental beliefs about the divine. Monotheism centers on the worship of a single, supreme God, often seen as the creator and ruler of the universe. Religions like Judaism, Christianity, and Islam are prominent examples of monotheism. In contrast, polytheism involves the belief in and worship of multiple gods and goddesses, each with their own powers and domains. Ancient Egyptian, Greek, and Roman religions, as well as Hinduism and Shinto, are polytheistic. While monotheism often emphasizes a single set of scriptures and rituals, polytheistic practices can vary widely based on the specific deities and their associated myths and traditions. The concept of God in monotheism is typically one of omnipotence and omniscience, while polytheistic gods can have varying levels of power and influence. Some scholars suggest that early forms of monotheism may have evolved from henotheism, the belief in one primary god alongside other deities. Pantheism, which views God as identical to the universe, can also be considered a form of monotheism, though it differs in its understanding of the divine. Monogenesis theory. The Semitic languages are a family of related languages that include Arabic, Hebrew, Aramaic, and many others. They originated in the Middle East and have spread across the region over thousands of years. One interesting aspect of the evolution of Semitic language is the emergence of writing systems. The earliest form of writing used by Semitic-speaking peoples was hieroglyphic writing, which developed in Mesopotamia around 3200 BCE. This writing system was later adapted into the cuneiform script. Monogenesis theory. This theory posits that all Semitic languages and their writing systems stem from a single ancestral language spoken by a unified community in the Middle East. Proponents of this view highlight the significant similarities in grammar, vocabulary, and phonology across various Semitic languages as evidence for a common origin. In recent times, the monogenesis theory has gained less support due to the increasing complexity of linguistic research and the discovery of more diverse linguistic data. Polygenesis theory. This theory suggests that different Semitic languages and writing systems evolved independently, each with its own unique history and development. Some linguistic evidence, such as variations in phonological systems and grammatical structures, supports the idea of independent development. The polygenesis theory has gained more traction in recent years as linguistic research has advanced and new insights have emerged. The debate between the monogenesis and polygenesis theories of the origins of Semitic languages and writing systems can be interpreted as a one versus many question. In this context, the debate revolves around whether all Semitic languages and writing systems have a common origin monogenesis theory or if they developed independently from each other polygenesis theory. This question can be connected with various other research areas within linguistics and anthropology. For example, it can be related to the origins of human language as a whole. Researchers in linguistics and cognitive science have long debated whether there was one universal language from which all other languages diverged, monogenesis theory, or if languages independently evolved in various regions, resulting in the tremendous diversity we see today, polygenesis theory. Another area where this question can be explored is in the emergence of culture and societal complexity. Some researchers suggest that certain cultural practices and social structures may have a single origin or a limited number of origins, while others argue for multiple independent developments. Base 10 log 10 has been widely used in the representation of semantics and diacritics in various fields, including linguistics, mathematics, and computing. For example, log 10 can be used to calculate the frequency of diacritic usage in a language, or to measure the semantic distance between words with different diacritic markings. In addition, Base 10 is also useful for creating indices or sorting diacritic markings based on their numerical values. This way, diacritics can be organized and compared easily, facilitating the study and analysis of linguistic patterns and structures. One-to-many relationships signify a single entity connected to multiple instances of another. For instance, a parent node in a tree data structure can have many child nodes, or a country can have many cities. Many-to-many relationships are more intricate, involving multiple instances of one entity connected to multiple instances of another. In a social network, a user can have many friends, and a friend can be friends with many users. This relationship is often represented using a junction table in databases or adjacency matrices in graph theory. These concepts are crucial in various fields like database design, algorithm development, and machine learning, enabling us to model and process complex real-world scenarios effectively. de Rham cohomology is a powerful tool in mathematics, particularly in differential geometry and topology, that allows us to extract topological information from the differential structure of a smooth manifold. At its core, de Rham cohomology is concerned with differential forms on a manifold. A differential K-form is a mathematical object that assigns a number to each oriented K-dimensional tangent space of the manifold. For instance, a zero form is simply a smooth function, while a one form can be thought of as a generalization of a gradient field. One of the fundamental results in de Rham cohomology is the de Rham theorem, which states that the de Rham cohomology groups of a smooth manifold are isomorphic to the singular cohomology groups with real coefficients. This theorem establishes a deep connection between differential geometry and algebraic topology. Hodge's postulates. One-line segment postulate: a straight line segment can be drawn joining any 2 points. Two-line extension postulate: any straight line segment can be extended indefinitely in a straight line. Three-circle postulate: given any point and distance, a circle can be drawn with that point as the center and the distance as the radius. Four-right angle postulate: all right angles are congruent. Five-parallel postulate: if two lines intersect a third in such a way that the sum of the interior angles on one side is less than two right angles, then the two lines eventually intersect on that side. Postulate 5, this is often referred to as the parallel postulate and is the most controversial of Euclid's postulates. It's essentially a statement about the nature of parallel lines. Hodge's perspective: Hodge's interpretation aligns closely with Euclid's original work. He emphasizes the fundamental geometric concepts of points, lines, circles, and angles. His focus on the fifth postulate highlights its crucial role in Euclidean geometry. Modern terminology: while Hodge used older terminology, modern mathematics often employs terms like acute, obtuse, and congruent to describe angles and shapes. However, the underlying concepts remain the same. Singular homology is a mathematical tool used to study the shape and structure of topological spaces. It assigns algebraic invariants, known as homology groups, to these spaces. The dimension axiom states that the homology of a single point is trivial in all dimensions except for dimension 0. The type of coefficients used in the homology theory is determined by a coefficient group G, which can be integers, rational numbers, real numbers, complex numbers, or integers modulo a prime number. The notation Hx, G represents the singular homology of a topological space X with coefficients in G. The first Chern class is a fundamental concept in algebraic geometry and topology, used to classify complex line bundles over a complex manifold. It's a topological invariant that captures information about the curvature and twisting of the bundle. It's a topological invariant, meaning it doesn't change under continuous deformations of the underlying space. The first Chern class of a line bundle L over a complex manifold X is an element of the second cohomology group of X, denoted as H2X, Z. In differential geometry, the first Chern class can be related to the curvature of a Hermitian metric on the line bundle. Complex K-theory focuses on vector bundles over complex manifolds, with applications in algebraic geometry and topology. Quaternionic K-theory, similar to complex K-theory, but considers quaternionic vector bundles. K-theory with coefficients generalizes K-theory by allowing coefficients in an abelian group. Self-conjugate K-theory, a variant of K-theory with additional structure. Connective K-theories, truncated versions of K-theories. KR theory, defined for spaces with involution. Bordism and cobordism theories, study manifolds up to cobordism equivalence. Stable homotopy theory, studies the stable homotopy category of spectra. Unoriented cobordism, studies unoriented manifolds up to cobordism. Complex cobordism, studies stably almost complex manifolds. Oriented cobordism, studies oriented manifolds up to cobordism. Special unitary cobordism, studies special unitary manifolds. Spin cobordism, studies spin manifolds. Symplectic cobordism, studies symplectic manifolds. Clifford algebra cobordism, studies manifolds with Clifford algebra structures. PL cobordism and topological cobordism, studies piecewise linear and topological manifolds. Brown-Peterson cohomology, a summand of complex cobordism localized at a prime. Morava K-theory, a family of cohomology theories related to formal group laws. Johnson-Wilson theory, a family of cohomology theories related to Brown-Peterson cohomology. String cobordism, a complex-oriented cohomology theory related to string theory. The first Chern class is a fundamental concept in algebraic geometry and topology, used to classify complex line bundles over a complex manifold. It's a topological invariant that captures information about the curvature and twisting of the bundle. It's a topological invariant, meaning it doesn't change under continuous deformations of the underlying space. The first Chern class of a line bundle L over a complex manifold X is an element of the second cohomology group of X, denoted as H2X, Z. In differential geometry, the first Chern class can be related to the curvature of a Hermitian metric on the line bundle. Complex K-theory focuses on vector bundles over complex manifolds, with applications in algebraic geometry and topology. Quaternionic K-theory, similar to complex K-theory, but considers quaternionic vector bundles. K-theory with coefficients, generalizes K-theory by allowing coefficients in an abelian group. Self-conjugate K-theory, a variant of K-theory with additional structure. Connective K-theories, truncated versions of K-theories. KR theory, defined for spaces with involution. Bordism and cobordism theories, study manifolds up to cobordism equivalence. Stable homotopy theory, studies the stable homotopy category of spectra. Unoriented cobordism, studies unoriented manifolds up to cobordism. Complex cobordism, studies stably almost complex manifolds. Oriented cobordism, studies oriented manifolds up to cobordism. Special unitary cobordism, studies special unitary manifolds. Spin cobordism, studies spin manifolds. Symplectic cobordism, studies symplectic manifolds. Clifford algebra cobordism, studies manifolds with Clifford algebra structures. PL cobordism and topological cobordism, studies piecewise linear and topological manifolds. Brown-Peterson cohomology, a summand of complex cobordism localized at a prime. Morava K-theory, a family of cohomology theories related to formal group laws. Johnson-Wilson theory, a family of cohomology theories related to Brown-Peterson cohomology. String cobordism, a complex-oriented cohomology theory related to string theory. The spectrum KO represents the underlying algebraic structure of real K-theory. The coefficient ring πIKO describes the algebraic structure of the theory itself. It has a periodic structure with period 8, meaning that the groups repeat every 8 dimensions. Ko0x is the group of stable equivalence classes of real vector bundles over a space X. This means that two vector bundles are considered equivalent if they differ by a trivial bundle. This fundamental theorem in K-theory implies the eightfold periodicity of the K-groups. M-theory is a theoretical framework that attempts to unify all fundamental forces of nature. One of its interesting aspects is the emergence of E8 symmetry in certain contexts. In the context of M-theory, K-theory plays a crucial role in understanding the properties of certain physical theories. The connection between E8 and K-theory arises from the fact that E8 symmetry can be used to describe the structure of certain K-theory classes. In particular, the E8 gauge theory, which is a fundamental ingredient of M-theory, is intimately related to K-theory. Most programming languages are decidedly inferior to mathematical notation and are little used as tools of thought in ways that would be considered significant by, say, an applied mathematician. The thesis is that the advantages of executability and universality found in programming languages can be effectively combined, in a single coherent language, with the advantages offered by mathematical notation. It is important to distinguish the difficulty of describing and of learning a piece of notation from the difficulty of mastering its implications. For example, learning the rules for computing a matrix product is easy, but a mastery of its implications such as its associativity, its distributivity over addition, and its ability to represent linear functions and geometric operations is a different and much more difficult matter. Indeed, the very suggestiveness of a notation may make it seem harder to learn because of the many properties it suggests for explorations. Users of computers and programming languages are often concerned primarily with the efficiency of execution of algorithms, and might, therefore, summarily dismiss many of the algorithms presented here. Such dismissal would be short-sighted since a clear statement of an algorithm can usually be used as a basis from which one may easily derive a more efficient algorithm. Kenneth E. Iverson. If spirit is an abstraction, a conjecture, a chimera, matter is an abstraction, a conjecture, a chimera, for we know as much, or rather as little of one as of the other. We may read Cudworth, Clerk, Leibniz, Berkeley, Hume, Bolingbroke and Priestley and a million other volumes in all ages, and be obliged at last to confess that we have learned nothing. Spirit and matter still remain riddles. Define the terms, however, and the controversy is soon settled. If spirit is an active something and matter an inactive something, it is certain that one is not the other. We can no more conceive that extension or solidity can think or feel, or see, or hear or taste or smell, than we can conceive that perception, memory, imagination or reason can remove a mountain, or blow a rock. This enigma has puzzled mankind from the beginning, and probably will to the end. Economy of time requires that we should waste no more in so idle an amusement. John Adams. This inaugural issue of the Journal of Landing Across Linguistic Foreground represents a first step in a long-term endeavor to reimagine the boundaries of human inquiry. We have presented a framework for exploring the intricate relationship between language, cognition, and the pursuit of knowledge, with a specific focus on addressing some of the most challenging problems facing humanity. The journey ahead promises to be both exhilarating and demanding. It will require us to embrace new ways of thinking, to challenge established assumptions, and to cultivate a deeper understanding of the subtle nuances of language. We invite readers to join us in this exploration, to engage with the ideas presented in this issue, and to contribute their own insights and perspectives. By fostering a vibrant community of scholars, thinkers, and innovators, we can collectively push the boundaries of human understanding and pave the way for a brighter future. The Journal of Landing Across Linguistic Foreground commits to ongoing dialogue and collaboration, fostering a platform for the exchange of ideas and the advancement of knowledge. We believe that through collective effort and a willingness to explore uncharted territories, we can unlock new insights and achieve breakthroughs that would otherwise remain elusive. This is merely the beginning of our journey. We look forward to the continued evolution of this journal and the exciting discoveries that lie ahead.
On the edge of reading in the halls of math, equations untamed like a genius's wrath. 7 riddles haunt the academic night, in shadows they linger out of pure spite. Unsolved millennium, don't you see? Whispers of infinity, as wild as can be. Dance on the numbers, spirals end and start. Hold like a key to the universe's heart. A prisoner's dream in a realm untold. Women's ghost in the Zeta fold. P versus NP, who will take the crown in this mental race, wearing logic's gown. A prison enters through a lattice maze. In the mirror, truth with theories days. Grasp the fear and dream it wide and far. Mysteries untangled under the cosmic star. Unsolved millennium, don't you see? Whispers of infinity, as wild as can be. Dance on the numbers, spirals end and start. Hold like a key to the universe's heart. Quantum loops in a quixotic ride. Ghosts of Godel, they will not abide. Mathematical beasts in shadows lair. In every fractal path, truth laid bare. Unsolved millennium, don't you see? Whispers of infinity, as wild as can be. Dance on the numbers, spirals end and start. Hold like a key to the universe's heart. Quantum loops in a quixotic ride. Ghosts of Godel, they will not abide. Mathematical beasts in shadows lair. In every fractal path, truth lays bare. Whispers of infinity as wild as can be. It's all the numbers, spirals, end and start. Hold the key to the universe's heart. I'm tasting answers to a lattice maze, in the mirror of truth where theories days. Grasp the fear, I'm dreaming wide and far. Mysteries untangled under the cosmic star. Quantum loops in a quixotic ride. Ghosts of Godel, they will not abide. Mathematical beasts in shadows lair, in every fractal power.